Hello and welcome to today's class. So, in today's class, we are going to perform reverse uh, calculation of logarithms, and that is what we call antilogarithms. So, what happens when you are given the logarithm of a number, of course, to the base of 10? We are talking of numbers only to the base of 10. What happens when you're giving the logarithm of a number to the base of 10 and you are told, let's say, to find that number? Let's say, for example, of course we are talking of numbers all to the base of 10. If I gave you the number 2 and I told you that it was a logarithm, all right, and I wanted you to find its antilog, all right, basically I want you to find the number that when I raise I want you to find the number that I'll get if I take 10 raised to 2. All right. So what would that number be? Of course, we know that that number would be 100, because when you raise 10 to 2, you get 100. So basically, antilogarithm is the process of finding this number 100 here, okay, when you are only given the logarithm, when you're only given the logarithm. So you are given the log and you are asked to use the log to then go ahead and find the number that we expect to find if, of course, the base 10 is raised to that particular logarithm. All right. So we are going to do antilogarithms using tables. All right. So in this diagram that you're seeing in front of the camera right now, we are having an antilogarithm table, of course, the base of 10. This table has 3 sections. We have the first section, of course, where we have the x column. All right. You will notice that in the x column, we are having numbers with 2 digits. All right. Of course, all of them beginning with a decimal point. So it is point, all right, 0.10 going on to 0.99. All right. And of course, I also want you to note that all the numbers in this antilogarithm table are supposed to be in 4 significant figures. So the first 4 numbers we get in the x column, or the first 2 numbers we get in the x column. Then the next 2 remaining numbers we get in the middle section, where we are having numbers running from 0 to 9. All right. So here is where we get the third digit of let's say the logarithm that should be given. All right, or running from 0 to 9. And then finally, for us to find let's say, logarithm of numbers which has 4 significant figures, we use the last section, that is the add section, where we find the number that actually gives us value for the fourth number within the 4-figure number that we are dealing with. All right. So anyways, that is basic introduction to what an antilogarithm table would look like. Why don't we go ahead and handle an example based of what you already know about antilogarithms. Now, so let's say that you are supposed to find the antilog, all right, of the number 0.5490. You are supposed to find the the logarithm of the number you're supposed to find the antilog of this logarithm 0.5490. So how would you go ahead and approach this? So the first thing you want to do, you want to write this logarithm using index notation. You want to write this logarithm using index notation. So basically what we're going to do, we want to first of all differentiate the characteristic and the mantissa. So where do we have our characteristic? Where do we have our mantissa? And we're going to write both of them to the base of 10. Remember, we are dealing with only numbers to the base of 10. So here is our characteristic, that is 0. So we are going to write that in index notation. Of course, that therefore means that our base is going to be that of base 10, as that is our standard base in this particular problem. All logarithms and antilogarithm tables are written usually to the base of 10. So therefore, we are going to have 10 raised to the characteristic. So that's going to be 10 raised to 0, of course, times, all right, 10 raised to the mantissa. All right, so whatever number we have after the decimal point is what we call the mantissa. And so it's going to be 10 raised to 0.54, right? 90. Or if you like, you can just go and say 10 raised to dot 5490. So basically what we have done here is we've rewritten the number 0.5490 in its index form, because remember, when you remember the laws of indices, because these are same basis, if we were to multiply them, then we would have to add these two numbers, the indexes. So 0 plus 0.5490 would just give us the same index that we are seeing there. All right, now that we have it in this particular format, we are then going to go ahead and basically simplify whatever we have in the right hand side. So we know that any number raised to 0 will always be equal to 1. So 10 raised to 0 is going to be equal to 1, and times. Now, for us to find a single number from this, basically we are going to have to find the antilog. We're going to have to read the value of what we'd get from raising this from the table. So what would be the antilog of 0.5490? So going to the antilogarithm table, I want you to find the first two digits of this particular logarithm. And so that's going to be 0.54. All right, so we're going to go to the x column and we look for 0.54. You can clearly see where 0.54 is. Then we are going to move to the right of 0.54 and find the third digit, that is 9. You remember it is 0.549. So we're going to go and after we've located 0.54 in the x column, move to the right and find the number we have under the column of 9 in the midsection. Of course, notice that that number is going to be 3.540. That number is going to be 3.540. Okay, and given that the fourth figure is 0, all right, when you look at the add section, the numbers begin from 1 to 9. So we do have 0. So basically that means that we are going to stick with the number that we will get under the column of 9, that is 3.50 as our antilog. And therefore the antilog of 0.5490 from the antilogarithm table will be 3.540 as we have seen in that particular scenario. So after we've done that, we'll come and basically multiply 1 by the number that we found from our antilog table. And notice that that is going to give us 3.540. All right, that's going to give us 3.540. And that therefore is our answer. So this is the antilog of 0.5490. So what basically this means is that if you were to take 10 and you were to raise it to whatever we had as our logarithm, that is 0.54, okay, 90, you will get whatever we have here, that is 3.540. So that is what this actually means. Very simple. Let us tackle the second example and see what we get. Awesome. For the second example, we have been told to find the antilog of the number 2.6107. So the first thing you want to do, you want to write this in index notation. Of course, for you to do that, you want to identify your characteristic and what your mantissa is. So I want you to note that our characteristic in this particular case is the number after the decimal point, and that is 2. All right, so because we are dealing with numbers all to the base of 10, we are going to raise the characteristic 10 to the characteristic, and that's going to be 10 raised to 2. All right, times, of course, 10 being the base, whatever we have as the mantissa, and that is going to be 0.6107. Remember, the mantissa is the number that we find after the decimal point. So given that our antilog table has been written with to the base of 10, so that is why you are seeing that we are writing our our index notations, of course, to the base of 10, which is then easier for anyone to go ahead and understand. All right. Okay, so we all know that 10 raised to 2 is going to be 100. Okay, so 10 raised to 2 is going to be 100 from whatever we're seeing here. Okay, and so it's going to be 100 times whatever number we find as the antilog of 0.6107, which happens to be the logarithm based off whatever we had earlier on when we separated the mantissa. So what you're going to do basically is go to the antilogarithm table, of course, which is to the base of 10. Find the first two digits, that is 0.61 in the x column. So you will note that 0.61 has been highlighted in this table. And so we are going to go to the right, of course, where we are having 0. Remember, the third digit of our number is 0. It's 0.610. Okay, so we're going to move to the right and record the number that we are having, all right, in the midsection where we are having 0, and that number is 4.074. I'll repeat, the number is 4.074. But remember that we are supposed to find the anti-logarithm of a 4 significant figure, that is 0.6107. So far we've only found the antilog up until 0.610. So for us to find the value for 7, we're going to go to the add section where we have column 7. So whatever number we are having under the column of 7 is what we will add to 4.074. And when you move down the 7th column in the add section, notice the number there, of course, in the same line as 0.61, all right, is actually 7. So we are going to add 7 to 4.074, and when you do the math, you realize that you are going to get 4.081. So that is what we will write as our antilog for 0.6107. So it's going to be 100 times 4.081. And so the antilog of the whole number is going to be 408.1. So what this basically means is that if we were to take 10 and we were to raise it to 2.6107, which is the number you're seeing here, then we would get 408.1. So the process of getting 408.1 is what we are calling anti-logarithm. Okay, that of course, and we are reading it from the table. Okay, let's go ahead and do the last example. Then we call it a day. All right, so for our last example, we're going to handle a special number. So we are going to handle the antilog of a bar number. All right, a bar number. So what if you told to find the antilog of 4 bar 4, all right, 0.5441, bar 4.5441. The principle doesn't change. What you first have to do is write this using index notation. Of course, that therefore means that you have to first of all identify what our mantissa will be, our characteristic will be, and our mantissa, of course, and all will be written to the base of 10 because our, of course, tables are written into the base of 10. So that's going to be 10 raised to our characteristic, which in this case is going to be negative 4. So it's going to be 10 raised to negative 4, all right, times 10 raised to 0.5441. All right, so now that we have you here, all right, I want you to note that 10 raised to negative 4 is basically the same as 10 raised to 1 all over 10,000. Okay, 1 over 10,000. Of course, this is a fraction here. All right, and so it's a fraction of 0.0001. All right, so anyways, maybe if I just write it, then it becomes easier for you to understand what I'm talking about. So it's going to be 1 all over 10,000. All right, 10 raised to 4 is basically 10,000. So it's going to be 1 all over 10,000, all right, times whatever we find as the antilog of 0.441, all right, 0.5441. So we're going to go to the table and find the antilog of 0.5441. So we go to the x column and find the first two digits. That's going to be 0.54. All right. So where we have 0.54, move to the right and find 4, which is the third figure. All right, and find 4 in the. Okay. So we will move to the right to the column of 4, and that number there is going to be 3.499. But remember, these are 4-figure number, so we have to find the value for 1, and therefore that means that we move to the add section where we have 1, and the number we have under the column of 1, of course, is 1. So we're going to add 1 to 3.499, and when you do that, you will get 3.500. All right, therefore that means that for us to find the antilog of this number, it's going to be the number that we get when we multiply, of course, this here. So that's going to be 0. Okay, all right. So basically 0. I don't know if I have to do that. Let me just go ahead and do it. It's going to be 0.100. Okay, 0.35. All right. So basically 1 all over 10,000 times 3.500 is going to be 0.00035, and that is going to be our antilog. So basically this means that if you were to take 10 and you were to raise it to above 4, okay, 0.5441, then what you get would be 0.00035. So that is it for this particular class. If you have any question, put it in the comment section, and I'll get back to you as soon as I can. See you and have a wonderful day.